Hello, my name is Andrew Greiner and this is Lab 5. The scene that I chose to explore is this incredible goal by the soccer player Roberto Carlos against the French national team. For that shot to go in, the physics had to be perfect behind that ball. So let's dive in and explore the physics principles behind that shot. The objective of this lab is to calculate the forces acting upon the ball while it is in the air, as well as the force of the initial kick. As a result of the lab, I successfully calculated the forces acting upon the ball while it was in the air that contributed to the curved motion of the ball, as well as the initial kick, the force of the initial kick. The contents of the video are the introduction, the description of the physics principles used, the explanation of how I collected the data, the presentation of the computational model, the explanation of important bits of code, and a conclusion. The main physics principle used in this lab is Newton's second law. It does two important things. One, it relates F net to the change in position over change in time of an object, and it is able to update the velocity of an object given a force. And we will use this in our computational model. We will also use a component form of F net, which splits F net into its parallel and perpendicular components. The parallel component represents a change in speed, while the perpendicular component represents a change in direction. The only force that comes into play while the ball is in the air is F spin. Technically, this is not a force acting upon an object, but it does change the motion of the ball while it is in the air. In order to determine the forces acting upon the ball while it is in the air, I decided to work backwards and determine these forces from motion data, just like in the black hole lab. However, when I tried to track the data, I noticed that the angle of the video was odd, so I could not track it accurately. So instead of that, I decided to create a graph that accurately modeled the motion of the ball. To make this graph, I needed a few important bits of information, which I got from another video which analyzed this goal. I found the distance from the initial position to the final position, from here to here, the initial position to the goal line, which is from here to the line, the approximate length of the curve, which is the size from which this deviates from its starting position and its top position in the middle, the time elapsed from the kick to the goal, and the velocity of the ball preceding the kick. This is the graph that I created to represent the motion of the ball in the air. The x-axis in this graph represents the goal line, so the data above the x-axis can be ignored. The starting position of the ball, where Roberto Carlos kicked it, is at x equals 0, approximately 0.33 meters from the goal line, and ends back at the goal line at x equals 29, which represents 29 meters of motion. This elliptical path, where it is curled, represents the curl of the ball while it is in the air, curling approximately 1 meter away and back to the goal line. After placing the position data from the elliptical graph into a CSV file and tweaking the code from the black hole lab, this is the resulting run of my computational model. I placed visual aids into the code in order to help you visualize the motion of the ball. The blue arrow represents the perpendicular force on the ball, and the yellow arrow represents F net. They are basically the same size because the parallel component is not very large because the ball is not speeding up, it is only changing direction. This is the most important code for my computational model. In my system properties, I set the mass of the ball to be 0.4 kilograms, which is the standard mass of a soccer ball. And then I created a variable to represent the velocity preceding the Roberto Carlos's kick. For my delta t value, I placed the total time of the kick, 0.93 seconds, and divide that by the number of position values in my CSV file. This way, after iterating over all of the position values, the time value will be 0.93 seconds. For my while loop, this calculates all of the force values acting upon the object. To find F net, we set that equal to dp/dt, which is Newton's second law. To find dp/dt, we subtracted two adjacent momentum values from each other and placed that over delta t. To find F net parallel, we found the change in the magnitude of dp/dt and placed that over delta t. To find F net perpendicular, we simply subtracted dp/dt total minus dp/dt parallel, which represents the component form of Fnet and dp/dt. To find the force of Roberto Carlos's kick, I added in this bit of code here. So I manipulated Newton's second law to solve for Fnet, which is represented in the variable Fkick here, and use the first velocity value as the final velocity and the initial velocity value as the velocity preceding the kick. As a result of running the computational model, I found that the force of the Roberto Carlos's kick was 4,100 newtons. This is a very strong kick because I found that the average shot of a soccer ball is usually around 3,500 newtons. I also found that the parallel component to F spin was 0.46 newtons, which is small in comparison to the perpendicular component of the spin, which makes sense because the speed of the ball is not changing considerably, but its direction is. So the perpendicular component was found to be 3.45 newtons, and the final velocity of the ball to be 31.57 meters per second.